Introduction to Geochemistry. Lecture 3 includes the structure and composition of the Earth. The topics to be covered in this lecture are the structure and composition of the Earth, the principal sources of information, geophysical approach, seismic data on Earth's interior, density and pressure distribution within the Earth, phase assemblage in the upper mantle, temperatures within the Earth, zonal structure of the Earth, composition of the crust, bulk composition of the Earth, the composition of the Earth as a whole, and relative abundances of elements in the crust. Coming to the structure and composition of the Earth, the principal sources of information. A knowledge of the composition and state of the Earth's interior, it's very essential to understanding geochemistry. So this problem, it cannot be solved by direct observation. Though the deepest boring at is made is one of about 10 kilometers, mines are still shallower, and apart from borings and mines, the only accessible parts of the earth are exposed on the surface itself. Some material it is brought to the surface by activities like igneous activity, but as we know only incompletely the depth from which it comes and whether it has undergone any second order changes, few deductions can be made from its evidence. Thus, in order to obtain or to understand the Earth's internal structure, we must go for an indirect approach. Here we turn to geophysics, where it can includes the application to the properties of the Earth to its several parts of the physical laws, dealing with what we know the gravitation, wave transmission, heat deduction, and then the constant of precession of equinoxes from which the Earth moment of inertia can be determined, or density distributions within the Earth, laboratory determination of elastic constants of various rocks, and the probable abundance of elements, etc. The geophysical approach it includes application to the physical properties of the Earth. To be acceptable, any theory must be consistent with the data which is available. However, the data may permit of several interpretations, none of which will formally conflict with what known about the Earth. So, current ideas on the Earth's internal constitution are certain to be modified by the discovery of the new facts and the improvement of existing knowledge. So, this geophysical approach it includes the physical laws dealing with gravitation, wave transmission, heat conduction, and other phenomena. Coming to the seismic data on the Earth's interior, much information about the Earth's interior is derived from the analysis of the seismic waves or earthquake waves. An earthquake generates waves of various kinds, of which there are two types that pass through the body of the Earth, and these are the most important for our present purpose. So, these two types of waves travel with unequal velocity, even in the same medium, and the faster are those transmitted by vibrations in the direction of the propagation. So, these are very analogous to the sound waves in the air, and they are the first to be recorded by seismographs at an appreciable distance from the focus of the earthquakes, and these are called as primary or P waves or compressional waves, and they move in the form of compressions and rarefactions. And the slower waves are transmitted by vibrations at right angles to the direction of the propagation. So these are very similar to the light waves, and these are known as secondary or shear or S waves. And the velocity of P and S waves, they vary with the density and elastic constants of the material through which they pass, and they are subjected to reflection and refraction at surfaces of discontinuity. And by comparing the travel times of primary and secondary waves from the same shock arrive at different stations, travel timetables can be drawn from which the velocity of these waves can be calculated, and these are as a function of the depth they can be measured. So the figure depicts the velocity and P waves within the Earth. And what does it include says it shows that the interior of the Earth is clearly heterogeneous in the sense that at different depths, the material has different elastic properties. This has to be noted. At different depths, the velocity and there are different elastic properties. So this heterogeneity is not random, but it is present in zones which are separated from each other by discontinuities of greater or lesser sharpness. So two distinct first order discontinuities, that means a first order discontinuity, it is one producing an abrupt break in the velocity depth curve. It has been recognized by all geophysicists. So two major or first order discontinuities can be noticed, and the earth is thus divided into three parts: the crust from the surface down to the first discontinuity, that is also known as the Mohorovicic discontinuity or Moho, and the mantle from the base of the crust to the second discontinuity, that is known as the Witchard-Gutenberg discontinuity, and the core from the Witchard-Gutenberg discontinuity to the center of the earth. And the extinction of the S waves at the base of the mantle, this is particularly very significant. And what does it suggest? It suggests that the material of the underlying core, this lacks rigidity and it behaves as a liquid. Second order discontinuities are recognized within the crust, the mantle, and the core. And there is no general agreement on the number and positions of these discontinuities, and their interpretation, it is much less certain. Coming to the density within the earth, as we know that the average density is about 5.5, and the density steadily increases inwards from the crust to the core. And mean density of the surface rocks, it is 2.8, and the interior of the earth must have a density which is greater than 5.5 to account for that part of the earth as a whole. And the high density, it can be explained in different ways, and important ways are number one, a change in the physical state. That means the increase in density, it is due to the accumulation, or it is due to the contraction of the crustal material into very smaller volume under enormous pressure. And the other way, a change in the chemical composition, that means the increase in the density, then it is being due to the presence of heavy substances such as a heavy metal, maybe iron or nickel. And overall, we can say that the upper mantle, it has a density of 3.9, and lower mantle 5, followed by outer core 11 and inner core 12.9. Coming to the pressure distribution in the Earth's interior. So the pressure in the Earth's interior, it is around 3640 kilobars. And due to the pressure of the heavy materials like rocks and the metals like nickel and iron, the pressure also increases. And the pressure down, there is 5 to 6 million times the atmospheric pressure. And at such a tremendous pressure, along with a high temperature, the materials are tend to melt, and they are basically in a plastic state. What does it information? That means what does it infers? The deformation it is caused to those metals due to the immense stress, it is permanent. So for these reasons, the outer part of the core in the molten state, as metals melts on the application of high temperatures and pressure, according to the physics and material science. So the outer part of the core, it is in the molten state. So the figure, it depicts that the pressure distribution in the Earth's interior. Coming to phase changes in the upper mantle. So as we know here, the diagram, it indicates the phase assemblages with the changing zero pressure densities for a model of an upper mantle. So this has been suggested after Ringwood, and this has taken from the Origin of the Earth and the Moon in the courtesy of the Springer and Verlag. The region A, so it has there are different regions like A, B, C, D, E, F, G, and A region, it is the lithosphere, and region B is the asthenosphere, and a region of 300 to 400 kilometers depth, a rapid increase in the density and velocity. And Rickwood and his co-workers, they have identified pressure phase transformations. And pyroxene, it assumes a garnet structure. And we can see that olivine, it transforms to beta phase olivine, that is which is 8% denser than the alivine. And at 400 kilometers, calcium garnet it transforms to dense perovskite. And Mg to SiO4, here it changes to spinel. And in F and G regions, so this includes spinel to MgO, that means magnesium oxide transformation in the F region. And in the G region, garnet transforms to ilmenite. These are the important phase changes in the upper mantle, which are suggested by Ringwood. Temperatures within the Earth, it includes, as we know that the variation of the density and pressure within the Earth to a considerable degree of precision, but estimates of temperatures at depth are little more than the intelligent guesses. Direct observations in mines and boreholes, they show that temperature increases with the depth, although the rate of increase varies greatly from place to place. This variation, it differs from place to place, like the table, it includes the heat flow values for major physiographic provinces like oceanic basins, oceanic ridges, oceanic trenches, and other seas, and also Precambrian shields, etc. The average oceanic heat flow is approximately the same as the average continental heat flow. This was a surprising discovery. And a considerable fraction of the heat flow from the continents, this is accounted for the radioactive elements in the continental crust. And the oceanic crust is thin, it is less radioactive, and it is incapable of providing more than 10% of the oceanic heat flow. Using data on the distribution of radioactive elements in different rock types, it is possible to estimate the contribution of radioactive heat from the crustal rocks. This is this can be inferred from the table that heat production by igneous rocks. And these calculations indicate that the crustal rocks may contribute from 30 to 50% of the continental heat flow, and the remainder of the continental heat flow and the oceanic heat flow, it is deep heat from the Earth's interior. And an estimated geotherm or thermal gradient within the Earth and the melting relationships of mantle and the core material, it indicates that the close approach of the geotherm to the silicate melting point curve in the upper mantle, where basaltic magmas are generated in the outer core, which appears to be liquid nickel iron. And such curves are somewhat speculative, but probably they represent the thermal conditions in the Earth to the first approximation. The interpretation of seismic data, it provides a primary threefold division of the Earth into crust, mantle, and the core. Together with other geophysical evidences, these data also give some indication of the physical properties of the material making up three parts. It now remains to take plausible deductions as to be the actual constitution of the Earth's interior using both the above mentioned evidences and the other significant information such as the relative abundances of elements and the composition of the meteorites. So the crust is accessible to our observation in the upper part at least, and general agreement exists to its major features. So the crust overall, it is heterogeneous and it varies in thickness from place to place. Marked differences exist, especially between the continents and the deep ocean basins. The Mohawisic discontinuity, it is found at different depths in different geological environments. And explored oceanic basins, it is between 10 to 13 kilometers below the sea level. And under the continents, it is usually about 35 kilometers below the sea level, descending to the great depths below active mountain belts. The Earth's crust, it is like the skin of an apple, and it is very thin when comparison to the other layers. And the crust is only around 8 kilometers thickness under the ocean basins and about 32 kilometers or 35 kilometers thickness under the continents. The crust makes up about 1% of the Earth, and the crust of the Earth, it is broken into pieces, and these are known as plates. To interpret the seismic evidence on the continental crust as indicating two principal layers, an upper one of granite or granodiorite composition, thus corresponds to silica and alumina, and a lower one corresponding to basaltic. So this is also known as SEMA, that is rich in silica and magnesium. And more refined seismic work which is coupled with the geological heterogeneity, and this has largely refuted this concept of crustal layering. So the seismic and geological heterogeneity has refuted the concept of two layers like CL and CMA. So overall, the continental crust, it is a mosaic of sediments, metamorphosed sediments, igneous intrusions, and volcanics. And there is a gradual change in composition from granitic to gabbro can be noticed. And this overall we can say that the Earth's crust, it is an isostatic adjustment. The irregularities of the surface, it is being compensated by the distribution of materials of different density within the crust and upper mantle. The second major part of the Earth, the layer is known as a mantle. The moho or mohorovisic discontinuity, it separates the heterogeneous crust from the more homogeneous mantle, and this is marked by the sudden increase in the velocities of seismic waves. Upper mantle, to a depth of about 400 kilometers, is separated from the lower mantle by a transition zone. This is around 600 kilometers thickness. And the nature of the upper mantle and the transition zone, it has been the subject of intensive study, and there are so many speculations in recent years. And it is now realized that the key to many geological and geochemical problems, such as the origin of the magma, the triggering of the deep focus earthquakes, global tectonics, continental drift, all they lies in the upper mantle and the transition zone. And understanding of the nature of the upper mantle, it has been greatly increased by improved equipments and techniques for studying the minerals and rocks at high temperatures and pressures. So it is now possible to reproduce in the laboratory the physical conditions corresponding to the depths of 400 kilometers or more within the earth. So these experiments, they indicate that three rock types like dunite, peridotite and eclogite can be seen. Ringwood in 1975, he has correlated geophysical, geochemical and petrological information for the upper mantle composition, and he prefers an ultra basic model for the upper mantle with an overall composition corresponding to a mixture of 1 part of basalt to 3 parts of dunite, which he calls it as a pyrolite or pyroxene olivine rock. And fractional melting of this material or this pyrolite, it would provide the basaltic magma which has been copiously injected into and through the crust throughout the geological time and leave as a residual material. This is known as a dunite or peridotite. And the mineralogy of the pyrolite, it varies as a function of temperature and pressure. And Ringwood has shown that this material of composition, it could crystallize in 4 different distinct assemblages. And which he has suggested that the first assemblage, it includes olivine and amphibole. This is also known as amphibolite. And the second assemblage, it includes olivine, aluminum purpyroxene and plagioclase. This has been named as a plagioclase pyrolite. And the third assemblage, it includes olivine, aluminum purpyroxene and spinel. This is named as a pyroxene pyrolite. And the fourth assemblage zone, it includes olivine, aluminum purpyroxene and garnet, which he has suggested as a garnet pyrolite. So thus overall 4 distinct assemblages of pyrolite has been suggested by Ringwood. Geotherms in upper mantle, they considerably differ below the continents and oceans, and there are regional differences in the mineralogical composition of the pyrolite. So the inferred composition of the upper mantle below Precambrian shield areas, average continental areas and oceanic areas, it is illustrated in this figure. And this shows that under the Precambrian shields, the mantle consists to a considerable depth of dunite or peridotite with minor segregations of eclogite. And this layer is not as thick under the average continental areas, and it is thin or replaced by amphibolite under the oceanic areas. And beneath the dunite peridotite zone, there would be a lower density pyrolite zone. And evidence for such region, it is found in the low velocity seismic zone, which is observed below 100 kilometers. Other polymorphic transformations that might be expected within the mantle are the change of MgSiO3 from a pyroxene to an ilmenite structure and of silica, that is SiO2, to a rutile structure. And the rutile form of silica, it has been converted into stishovite, and this has been suggested by Stishow and Popova in 1961, and this has named as a stishovite, and this stishovite it is stable at 1.3 kb and 1600 degrees centigrade. And the magnesium iron silicate solid solutions, olivine spinel transitions, they occur in Mg2SiO4 at 130 kilobars and 600 degrees centigrade, and MgSiO3 it is probably converted into Mg2SiO4 and SiO2, that is also known as a stishovite, at 120 kilobars and at 500 to 2000 degrees centigrade. And all these transformations, they occur in the transition zone. Clark and Ringwood have applied these data to the elucidation of the transition zone, and as a first approximation, they assume it is essentially composed of magnesium oxide and silicon dioxide corresponding to a mixture of olivine, Mg2SiO4, and pyroxene, MgSiO3. And these phases would be stable to a depth of about 400 kilometers. And below that depth, a series of transformations into closer packed phases would have taken place. And in the light of available data, they postulate the following the transformations with the increasing the depth. So that is 2 MgSiO3, that is a pyroxene, it could be converted into olivine and stishovite. And also olivine Mg2SiO4, it could have been transformed to spinel structure, and the spinel and the stishovite has been transformed to ilmenite structure. And then this spinel, that is Mg2SiO4, it could be transformed to MgSiO3, that is ilmenite, and periclase, that is MgO. All these series of transformations, they would become complete around a depth of 1000 kilometers. They result in a density increase from 3.2 to 3.9. So this can be referred to zero pressure. And it is significant that the ultimate attainment of a close packed state, it involves successive transformations through several intermediate states, which is reflected in the considerable depth of the transition zone. And in addition, the mantle contains additional elements like iron, calcium, aluminium, and sodium, which are in atomic substitution in these principal phases. The lower mantle between 1000 to 2900 kilometer, it appears to be homogeneous, and presumably it consists of a mixture of magnesium iron silicate with ilmenite and magnesium iron oxide, or it includes periclase. And Ringwood suggested the possibility of ilmenite structure transforming to perovskite structure, that is CaTiO3 structure, and periclase structure to cesium chloride structure. And the concept of the iron core, it is based on the meteorites and seismic evidence. And there is a sharp change in the density in the mantle from 5.5 to 10 in the core. And the seismic discontinuities between the mantle and the core is very sharp. And this is also known as a Witcher-Gutenberg discontinuity. Coming to the composition of the core, as there is no passage of secondary waves in the core, it indicates that it could definitely be made up of liquid behavior or liquid material, and it cannot transmit secondary waves. It extends from 2900 to 4982 kilometers, and it constitutes of 17% of volume and 34% of the mass of the Earth. And the core is a homogeneous fluid, and the PV velocity decreases from 12.6 to 8.4 kilometers per second. And the outer core is very hot. That means it is around the temperature is around 4500 to 6000 degrees centigrade, and it is always molten. Coming to the middle core, so this is a transition layer between the outer core and inner core, and this middle core, it extends from 4982 to 5121 kilometers, and it is in fluid to semi-fluid state. And the inner core, it extends from 5121 kilometers to the center of the Earth, that means around 6371 kilometers. and it is in solid state. It consists of iron and nickel. And this iron core, it could transmit both the P and S waves, and its density around 13 and thickness is 1250 kilometers. And the inner core, it is even hotter. This is even up to 7000 degrees centigrade temperature can be seen, but it stays solid because the pressure is 6000 times greater than on the surface. Coming to the structure of the Earth's overall composition, the atmosphere and biosphere, what is this, the important chemical parameters in atmosphere and biosphere and hydrosphere, and the crust and mantle and the core. And this is the table displaying the volume and masses of the Earth's shells. Coming to the composition of the crust. The average composition of the crust, this is in effect that of igneous rocks, since the total amount of the sedimentary and metamorphic rocks is very insignificant in comparison to the bulk of the igneous rocks, and in any case their average composition, it is not greatly different. So Clark and Washington in 1924, they have estimated that the upper 10 miles of the crust consists of 95% of igneous and metamorphic rocks, 4% shale, followed by 0.75% sandstone and 0.25% limestone. Where sedimentary rocks are present, they form a relatively thin veneer on an igneous basement, where they locally thickened in orogenic belts. According to Ronov and Yaroshke, there are three types of the crust. So these are named as a continental, oceanic, and subcontinental. So the crust, it is predominantly made up of 8 elements. So these are oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Of these, oxygen is absolutely predominant, and as Goldschmidt first pointed out, the predominance is even more when marked when the figures are recalculated to atom percent and volume percent. So the table, it shows that the Earth's crust consists almost entirely of oxygen compounds, especially silicates of aluminum, calcium, magnesium, sodium, potassium, and iron. And in terms of numbers of atoms of oxygen, this exceeds 60%. And if the volume of the different atoms, or rather ions, is calculated, oxygen makes up more than 90% of the total volume occupied by the elements. So the crust of the Earth is essentially a packing of oxygen anions surrounded by silicon and the ions of the common metals. And that's why Goldschmidt, he has remarked that the lithosphere, it may well be called as a oxysphere. Some elements, although present in the crust in considerable amounts, they are systematically dispersed throughout the common minerals, and they never occur in any concentration. And these elements are known as the dispersed elements. This has been coined by Vernadsky. And coming to the examples, these are rubidium dispersed in potassium minerals and gallium in aluminum minerals. These are termed as a dispersed elements. Boltzmann introduced the term Clarke, defining the average percentage of an element in the Earth's crust. Thus, the Clarke of oxygen is 46.60, and that of Clarke of silicon is 27.72. In discussing dispersion and concentration of the elements, Vernadsky has introduced the term Clarke of concentration. So what is this Clarke of concentration? This Clarke of concentration, it is a factor showing the concentration of an element within a particular deposit or even within a particular mineral. Thus, suppose if we know the Clarke of manganese is 0.1, the Clarke of concentration of manganese in pyrolusite is 632, in rhodonite 419, and in silomelane with 50% manganese is 500. So this Clarke concentration factor, it is useful in consideration of the migration and deposition of the elements and in the discussion of ore deposits. An ore, it is simply a deposit in which the concentration Clarke of the element sought, it reaches a figure sufficient to make it the extraction profitable. So here the table, it shows or it depicts an evaluation of the concentration Clark necessary to form ore bodies of the commoner metals. Coming to the composition of the earth as a whole, the bulk composition of the earth is essentially it is determined by the composition and relative amounts of the mantle and the core because they make up over 99% of its mass. By using the deductions regarding the earth's interior discussed, and an average composition of the earth as a whole can be calculated. So for this purpose, the assumptions about the composition of the core and mantle can be made. The assumption number one, the iron alloy of the core has the composition of the average for nickel iron in chondrites, and it includes the average amount, roughly around 5.3% of iron sulfide in these meteorites or troilite in these meteorites. Coming to the second assumption, the composition of the mantle and the crust is the same as the oxidic material. That means it includes the silicates and small amounts of phosphates and oxides of the average chondrite. Ganapathy and Anders in 1974, they have calculated the bulk composition of the earth on a rather more elaborate set of assumptions, and their figures are included for comparison. The table, it indicates the calculation of the bulk composition of the earth. In view of the uncertainties and assumptions involved in calculation of this kind, too much weight should not be given to the numerical results which are obtained. However, some significant deductions of a semi-quantitative order are probably justified, and the results it indicate that 90% of the earth it is made up of four elements. So these are iron, oxygen, silicon, and magnesium. The other elements that may be present in amounts which are greater than 1%, it includes nickel, calcium, aluminum, and silicon. And seven elements like sodium, potassium, chromium, cobalt, phosphorus, manganese, and titanium, they may occur in amounts from 0.01 to 1%. Thus, the earth is made up almost entirely of 15 elements, and the percentage of all the others is negligible, probably 0.1% or less of the whole. The relative abundances of elements in the crust are included in the table for comparison with the bulk composition of the earth. So the main differences are the lesser abundance of iron and magnesium in the crust, and the non-appearance of nickel and sulfur, and the increased significance of aluminum, potassium, and sodium. So this suggests that the differentiation of the earth has led to the concentration of relatively light and easily fusible alkali aluminum silicates at the surface. Coming to the summary, structure and composition of the earth. This is based on geophysical evidence, seismic data, and meteorites. This data, it revealed that earth is threefold, that is, it is divided into crust, mantle, and the core. And the crust, it is heterogeneous, and it includes mosaic of sediments, metamorphosed sediments, igneous intrusions, and volcanics. And there is a gradual change in composition from granitic to gabbro can be seen in the crust. And the crustal rocks, they could contribute 30 to 50% of the continental heat flow, and the remainder of the continental heat flow and the oceanic heat flow, it is deep heat from the earth's interior. And density, slowly it increases from the crust to the core, and the pressure of the at the earth center, it is about 3640 kilobars. And the upper mantle, it has a composition of a pyrolite. That means it consists of 3 parts of ultramafic rock and 1 part of basalt. So it has 4 distinct phase assemblages. These are suggested by Ringwood, and these includes amphibolite, plagioclase pyrolite, pyroxene pyrolite, and garnet pyrolite. And mantle, it's a heat engine. It is responsible for ocean floor spreading, continental drift, orogeny, and major earthquakes and global tectonics. And the extinction of the secondary waves at the base of the mantle, it is significant. And the core, it consists of iron nickel alloy. And overall, the crust, it constitutes 8 elements. So these are oxygen, followed by silica, iron, calcium, sodium, potassium, and magnesium. And they make up about 99%. So as per the Goldschmidt's suggestion, so the crust is also known as a oxysphere. The Clark of concentration is a factor showing the concentration of an element within a particular deposit or even within a particular mineral. And the concept of dispersed elements, it was proposed by Vernadsky. So this it includes some elements, although present in the crust in considerable amounts, are systematically dispersed throughout common minerals and they never occur in any concentration. So these are known as the dispersed elements. And the bulk composition of the earth, it includes 90% of the earth. It consists of 4 elements. So these are iron, oxygen, silica, and magnesium. So these are the references. Thank you for your time. See you in the next video.